Hello guys, I'm Guru Prasad and currently I'm studying in SVC Bengaluru. I'm from ISC department. Today we are going to talk about some of the most important topic which is related to data structure and applications, that is the dynamic hashing and the leftist trees. So let's start the video. First, we are going to explain about introduction of dynamic hashing and leftist trees. What is dynamic hashing? Dynamic hashing is a technique used to effectively handle the hash table collisions by dynamically adjusting the size of hash table. Leftist trees are types of binary tree data structure that prioritize that nodes based on their leftist trees and leftist properties, ensuring efficient access and manipulations. This presentation will explore the concept of dynamic hashing and leftist trees and their application in various fields. Next, the overview of dynamic hashing is the dynamic hashing follows the for efficient handling for hash table collisions by dynamically resizing the hash table as needed. It is especially useful when the number of elements to be inserted or deleted from the hash table is unpredictable. Dynamic hashing ensures the more even distribution of keys, reducing the likelihood of collisions and improving overall performance. So we are going to handle the hash table collisions by dynamically and resizing the hash table as whatever we needed. So this is called as dynamic hashing. Next, what are the benefits of dynamic hashing? The first one is efficient handling of collisions by dynamically resizing the hash table, improved performance by maintaining a more even distribution of the keys. Next, the flexibility to handle the unpredictable changes in the number of elements. These are all the benefits of the dynamic hashing. Next, move on to the dynamic hashing techniques. How we can access the dynamic hashing. Extensible hashing, that is, or extendable hashing. Hash table size is a power of 2 and a directory structure is used to dynamically allocate and reallocate the buckets. Linear hashing is the hash table size grows linearly with the number of elements and splits operation is performed when a collision occurs. Next, dynamic perfect hashing achieves the zero collisions by using a two-level hashing structure and minimal space requirements. This is the accessing the way of dynamic.
This is one of the examples for the data records and the data buckets, which is the example of the dynamic hashing. For the 000 and 001, 010, 011, 100, 101, 110, 111, which is having all the records in the data buckets, that is 2, 4, 5, 9, 1, 3, 7, 6, which is having the related values, which is having corresponding names, that is B0, B1, B2, B3, B5, all are stored like a dynamic using the dynamic hashings. So 000 and the 100, which is both are having the 2 and 4, which is having the same value, which is stored in the data bucket. Next 001, which is stored in as a 59, and 010 and a 110, which is also stored as a 59 and a 13. Next 011 and a 111, which is stored as a 7. Next, the final one is the 6, which is stored by the 101. This is all how the all the data are stored from 0000 to 0000 to 111. Next, move on to the example for left histories. This is how the distinct of I, the node which is having the data, and distinct which is having the left and right, left child and right child. The distinct of the I, first which is having the 1, next which is having the 2, then 2 which is come back to the 1, next 1 which will go to the 0, after that 1 will go to the 0, and next time it will goes to the 0, after that it will backtrack and will come back to the 2, and next it is move on to the 1, next after that it is move on to the 1, before after that it will not go to the depth and it will backtrack and it will come back to the 1, and next it will go to 0, after that it will reach the end, there is 0, next it will roll back or track back, next it will backtrack and it will come back to the 1, next go to 1, after that it will go to 0, after that one more time it will backtrack and will come back to 1, next it will move on to the 1, after that finally it will move on to 0, then it will backtrack to 1, then after that it will finally move on to 0. This is how the leftist trees works, or the merging and the inserting adding process.
Caching. Next, leftist trees. What is leftist trees? Leftist trees are types of the binary tree data structure that prioritize the nodes based on their leftist priority. These are all the examples of leftist trees, which is having the binary tree, complete binary tree, full binary tree, perfect binary tree, which is having the leftist trees. So next, the leftist trees property states that the rank of any left child is greater than or equal to the rank of its right sibling. Next, the leftist property ensures that the left child of any node is always the one of the longest path of null node, providing the efficient access and manipulation. Next, what are the benefits of leftist trees? Leftist trees, which is having the leaf nodes, the length of the rightmost path is 2 in this example. Efficient access and a manipulation due to the leftist property. This is the one benefit, one of the benefit of leftist trees. Easy implementation and maintenance compared to the other balanced tree structure is the one more benefit of leftist trees. Next, suitable for application where the priority of the nodes is important, such as priority queues. In the priority queues, the leftist trees are very much important and it is very much used. Next, what are all the operations is performed based on the leftist trees? First one is we are going to combine two leftist trees into the single leftist trees while maintaining the leftist trees properties. Next, insert adds a new node to the leftist trees while preserving the leftist property. Next, delete, which is the removes a specific node from the leftist trees while maintaining the leftist property, that is delete. Next, the leftist trees merge operation. How can it will be done? The merge operations combine the two leftist trees into a single leftist trees. That is called as merging. It compares the roots of two trees and sets of the roots of resulting tree as a smaller one. In this example, we are going to merge a two leftist trees into the single leftist trees. Next, the merge operation then resources on the right child of the smaller root and the other tree, ensuring the leftist tree properties should be maintained. This is the example for the leftist trees, which is based on a merging operation. Next, move on to the insertion. The insert operation adds a new node to the leftist trees. It creates a new tree with a new node as its roots and merge it with the existing leftist trees. The resulting tree maintains the leftist property due to the merge operation. In this example, we have added the one like we are going to merge the two leftist trees. In this, we are going to insert and add like in the leftist trees how it will be added. Next, move on to the delete operation, which is the most important operation in the leftist trees. The delete operations removes a specific node from the leftist trees. First one is the initial tree, then F deleted. That is a in the case one the F is deleted. In the case 2A, then M is deleted. Then case 2C, then the G is the deleted. This is how the deletion operation could be done. The resulting tree maintains a leftist property due to the merge operation. This is the example for delete operations. Next, applications of dynamic hashing and leftist trees. Database indexing. Dynamic hashing allows for efficient indexing for a large databases, while leftist trees provides the efficient access to the indexed data. The dynamic hashing and leftist trees will be very much useful in the database indexing, which is while having the large amount of the databases. Next, priority queues. Priority queues, the leftist trees can be used in efficiently implement the priority queues where the priority of the elements determines their order of access. Next, file system. File system is dynamic hashing can be used for efficient file system organization, while leftist trees can be used for the efficient file retrieval. This is the example for the hash table in the data structure. Main thing in leftist trees are the priority of the node is determined by its key value. Then the node with the smallest key value is designated as the root node. The left subtree of the node in leftist tree is always larger than the right subtree based on the number of nodes in each subtree. This is known as the leftist property. One of the key features of the leftist tree is the calculation and maintenance of a null path length of the each node, which is defined as the distance from the node to nearest null or nearest empty child. The root node of the leftist tree has shortest null path length of the any node in the tree. Next, the main operations performed on the leftist trees includes insert, extract, minimum, extract min, extract merge, and extract min, extract max, and merging, inserting, adding, deleting. And the insert operation simply adds a new node to the tree, while the extract min operations removes the root node and updates the tree structure to maintain the leftist property. The Merge operation combines the two leftist trees into the single leftist trees by linking the root nodes and maintaining the leftist property. Next, move on to the advantages of leftist trees. The efficient extract min operations is the one of the most important advantage of the leftist trees. The extract minimum operations has to be done or has a time complexity of 0 or log n, making it one of the most efficient data structure for these operations. Next, the efficient merging. The merge operation has the time complexity of 0 or log n, making it one of the fastest data structure for merging the two binary heaps. Next, the third one is simple implementation. The leftist trees has the relatively simple implementation compared to the other binary heap data structures such as Fibonacci heaps. Next, this is all about the leftist trees, dynamic hashing, all those things. What are the operations performed on the dynamic hashing and the leftist trees? Next, we are going to conclude the presentation about the dynamic hashing and the dynamic hashing and the dynamic hashing and the leftist trees. The dynamic hashing and leftist trees are powerful data structure that provide the efficient handling of collisions and prioritize the node access. They have wide range of applications in the various fields, including database indexing, priority queues, and the file systems. Next, the understanding these concepts can be greatly improve the efficiency and the performance of the data storage and the retrieval systems. This is all about the data or the dynamic hashing and the leftist trees. So what are all the applications used? What are all the advantages and disadvantages of the dynamic hashing and the leftist trees? And what are the operations which is you perform the dynamic hashing and leftist trees? This is all about the dynamic hashing and leftist trees. So you have learned something, please utilize this one. So thank you all.